Out on the open ocean, weather can turn violently in a matter of minutes. Massive ocean swells can easily reach 30 feet, slamming into ships with enough kinetic energy to warp steel. Modern container ships navigate through this environment carrying absolute mountains of cargo. The largest vessels today can hold over 24,000 containers. We're talking about hundreds of thousands of tons of mass, holding upwards of $14 billion worth of goods on a single voyage. Stacking that much weight into towering columns creates a severe physical problem. It makes the vessel incredibly top-heavy. Every time a massive wave hits, the ship rolls, constantly fighting the threat of capsizing or having its entire load collapse sideways into the sea. Preventing this collapse depends on a hidden, highly precise architecture of geometry and structural steel, designed specifically to lock that massive load in place. To stabilize a top-heavy structure, you first have to pull the center of gravity downward. Ships use massive water ballast tanks built directly into the bottom and sides of the hull. Pumping thousands of gallons of ocean water into these lower cavities acts as a heavy anchor against the rolling motion. But keeping the ship itself upright is only the first step. You still have to secure the cargo deep inside the hold from violently shifting back and forth. As a crane lowers a shipping box, it slides perfectly down into 4 corner tracks. When the ship rolls aggressively, the massive lateral force pushes directly into these rails. The steel frame blocks any horizontal movement. Because the walls of the cell guides run the entire vertical length of the stack, containers packed down in the lower holds do not require any additional interlocking hardware to stay put. The internal hull functions as a massive, inescapable metal grid. It completely neutralizes the threat of cargo sliding around by boxing it in on all sides. However, the physical protection of the hull has limits. Once the lower holds are entirely packed, massive watertight hatch covers seal the deck shut, and the remaining containers have to be loaded directly on top, directly into the open air. This photograph, taken from the deck level during a storm, shows what happens when the protection of the hull disappears. Up here, there are no cell guides to shield boxes from heavy wind shear and massive ocean swells crashing right up against the outboard stacks. To keep these exposed stacks from simply toppling into the water, crews use a specialized mechanical connector known as a twist lock to physically bind the corners of the boxes together. This device slides tightly into an opening called a corner casting, located on the bottom of a container. As the heavy box lowers onto the container beneath it, the pressure mechanically forces an internal cone on the twist lock to rotate, binding firmly against the inner steel lip of the casting. Locking the corners vertically handles upward and downward motion, but a towering stack of metal boxes leaning sideways in a storm generates immense lateral strain. Under enough shear force, those corner castings would eventually tear right open. This photo illustrates the necessary countermeasure to that strain. Crews utilize reinforced platforms called lashing bridges, anchoring thick, diagonal metal rods directly from the ship's deck into the lower tiers of the containers, drawing them tight with heavy turnbuckles. Above deck, the defense shifts from the passive containment of the hull into an active, rigid web of localized mechanical tension. Beyond the physical locking hardware, there is a severe logistical hurdle. Looking at this dense mosaic of thousands of identical steel blocks from the stern, the scale makes it nearly impossible to manually locate a single specific container. Port operators and crane drivers solve this by mapping the entire vessel using a precise coordinate structure known as the bay, row, and tier numbering system. These numbers function exactly like an X, Y, and Z axis. The bay number targets the specific longitudinal slot from the bow to the stern. The row specifies the exact line across the width of the ship, moving outward from the center. Finally, the tier defines the precise vertical level in the stack. Without this strict mathematical framework organizing the ship's layout, perfectly securing thousands of boxes wouldn't matter. The cargo would effectively be lost the moment it was loaded on board. We build highly regimented matrices of steel, coordinates, and twist locks to tame the load, but then we send that perfect structure directly out into the most chaotic and unforgiving environment on Earth. Even with precise mechanical binding and thousands of pounds of lashing tension drawn across the lower tiers, this engineered architecture has physical limits. This image captures exactly what happens when the violence of the ocean exceeds those mechanical tolerances. Under a severe enough roll, The immense kinetic energy of top-heavy stacks can shear right through the steel locking cones and snap the lashing rods entirely, sending millions of dollars of cargo plunging straight into the sea. Maintaining the flow of global trade is an ongoing daily war between highly calculated human engineering and the unpredictable, crushing forces of nature.